All right. Well, welcome everybody. Thank you for coming. My name is Evan Sparks, and I'm a fourth year graduate student at the UC Berkeley AMP Lab. I study systems for large-scale distributed machine learning. I've been working on machine learning on top of Spark since 2012. And today I'm going to talk to you about optimizing Terascale machine learning pipelines with KeystoneML. A point to clear up some confusion before I get started. I am not Evan Apache Sparks. That's a different project. So I'm just Evan Sparks. Anyway, all right. So what is a machine learning pipeline? So a machine learning pipeline, if we kind of look at the textbook, it looks something like this. We start with our data, this raw data that comes from maybe it's images or something like that. I throw it through my classifier and now plops a model, and then I'm done, right? Well, not really. It's a little more complicated than that. I have to do this process of feature extraction. So I take my data, maybe it's in pixel space, and I get it into a space that my favorite machine learning algorithm can use as input, and then I'm going to train, say, a linear classifier in this case, and out comes a model. And then this model is the thing that I can then use to make predictions on real data. And so, of course, I have to actually do that. I have to make this model and featurization process available offline to some either online process that has to serve predictions very quickly, or some batch process. What does a real machine learning pipeline look like? Well, it looks more like this. So this is much more complicated than that 4 boxes I just showed you on the last screen. This is a real image classification pipeline proposed by Adam Coates and Andrew Ng just a couple years ago. The first, if we squint at it though, we see that all of these boxes kind of together, the first set of them anyway, do what we call feature extraction. So that's just like feature extraction from my last slide, only instead of one box doing feature extraction, I have all of these modular components chained together in kind of a nice way. These are going to be things that start as very domain specific. So starting with image parsing, maybe I'm going to normalize my images. I might throw these convolutional filters over my images to extract some features. And then I'm going to do some aggregation and some pooling, these things that are sort of general statistical operations before feeding into my favorite model, in this case, linear solver. And I'll talk a lot about linear solvers today, but they are just one tool in the sort of toolkit. And then again, I have to be really careful about how I do my feature extraction at test time. I have to, in fact, make sure that feature extraction at test time is exactly the same as at training time. And in order to compute some statistic of interest, call it test error, or just to make predictions, sort of online, I have to be very careful about how I do this. So great. So so far what I've shown you is really stuff that we can do on sort of a single machine. It might look like scikit-learn or many of the other machine learning frameworks that we've heard about before. So in my talk title, I talk about scale, and we're at Spark Summit, so we're really worried about scale. And so one question that comes up is, what about this is hard to scale? What can we scale sort of naively, embarrassingly parallel, pleasantly parallel, as I like to call it, and what is sort of fundamentally hard? So a lot of this stuff, a lot of the stages in this pipeline are really embarrassingly parallel. Of course, we can store our images in some distributed file system like HDFS. That's distributed, that's shared nothing. We can do parsing shared nothing. If we throw 1,000 cores at it, parsing a million images, it's probably going to go 1,000 times faster than if we did it on a single machine. Other steps of this pipeline, again, have this property where it's embarrassingly parallel over my data. Other parts of the pipeline are not so parallel. They are sort of blocking operations, things like normalization, where we might need to compute sort of average of every particular pixel value in an input image. The same pixel across all of my entire corpus. Same thing comes up in text processing all the time. So normalization is an example of something where we really have to have some coordination among all the workers in our cluster before we can fully execute that operation. So that stuff is, it requires coordination, but the communication requirements maybe aren't that heavy. Now, on the other hand, you have these things that are really tricky to scale, things like linear solvers or k-means clustering, where you have to sit down and think hard about what's the best distributed algorithm that we want to run in order to get these things to scale out nicely on our cluster of machines. The benefit to the design that we're proposing here with KeystoneML is that by encouraging the construction of pipelines that are built on these modular components, we can pick the components that we know are sort of hard to scale out, put our thinking caps on, focus really hard on scaling those out, and then the other stuff hopefully will scale out sort of for free. So that's the idea. And so what is KeystoneML? So KeystoneML is a software framework for building scalable end-to-end machine learning pipelines on Apache Spark. It's going to help us understand what it means to build systems for robust and scalable end-to-end advanced analytics. So from a research perspective, this is, what's the research objective here? We want to understand this new class of workloads and understand what's the system support we need to build in to help users, really get the best performance out of their systems and prevent them from, rebuilding these same things over and over again. Shipping with this system are a bunch of example pipelines that achieve state-of-the-art results on many large-scale data sets in computer vision, NLP, and speech. These are pipelines that we lifted from academic papers, recent academic papers, where we said, okay, let's rebuild this thing as it's written in the system and see how well we can scale these things up. And it is open source software. It's available at keystone-ml.org. We're on version 0.3, released a couple months ago, and the next version is in the works, coming down the pipe soon. So great. So I've talked a little bit about pipelines, and now I want to give you a few examples of the kinds of pipelines you can build in KeystoneML, some of the examples that ship with the system, to sort of motivate that this works across a variety of different problem domains before I dive into the details of how we optimize these things. So the first example is text classification. So in a text classification pipeline, you might start with these domain-specific operators geared toward text. So these are things like trimming off white space, maybe tokenizing, breaking my words up into a bunch of tokens. I might do some text-specific feature extraction, things like bigram extraction. That's just the words that are right next to each other. And then I get to the stage of my pipeline where the learning begins to happen. So first is this top features estimator, as we call it in the system. So this is really just taking, say, the top 100,000 most common words in my corpus and using that to project my feature space onto. Another learning algorithm we might want to do is naive Bayes classification. So that's a bread and butter sort of machine learning algorithm. And then this thing, naive Bayes, gives you a probabilistic output when making its predictions. So maybe we just want to take the max, the most likely class that it spits out. And that's going to be our pipeline. Now, of course, we have to fit this thing to some training data. So we have to, when we're doing machine learning, of course, we have to learn based on some training examples. And once we do that, though, out comes a pipeline that's sort of end-to-end, a series of transformations to my data that starts with featurization and the output of which is a prediction. So to write this pipeline down in Keystone, it's roughly the same number of lines of code that the developer has to write as there are sort of boxes on my screen. So the developer experience is chaining together these estimators and transformers into a pipeline that we then fit to data. And as I mentioned, once the pipeline has been estimated, that is, it's been fit to this data, we now have an object that we can ship around. It's serializable. We can ship it around to, say, a model server like Velox, which many of you may have heard about. So great. So here's a not-so-simple pipeline that's for image classification. And this looks a bit similar to the one I showed you before, but there are some notable differences. So again, we're going to do some domain-specific pre-processing on our images. We're going to resize them. We're going to convert them to grayscale because in this pipeline, we don't care about color information. SIFT features are sort of a bread and butter computer vision feature that we can extract from images. And then we get into these statistical transformations, things like PCA for dimensionality reduction or whitening, Fisher vectors, which is sort of, you can think of it as a similarity metric that we compute across our image features, and then bread and butter sort of linear regression. And again, we're going to fit this to some training data, and out is going to come a prediction pipeline. And again, to write this pipeline down, it takes about as many lines of code as there are boxes on the screen. We can run this on this VOC data set, which is several years old and rather small, but still actually a fairly beefy learning problem. And the nice thing is that we have this pleasantly parallel featurization and evaluation, and we have to be a little bit clever about how we distribute our solves and so on within this pipeline. The bottom line is we can run this thing end to end in about 7 minutes on a modest cluster and achieve the performance of the people who wrote down this pipeline, who proposed this pipeline in the first place a few years ago. And that's by contrast with a couple of hours in a highly specialized code base, which we'll get to in more detail in a bit. So an even less simple example is this IMAGENET pipeline. This is a pipeline that uses both color information and edge information to generate its features. We can write down this whole IMAGENET pipeline in just a handful of lines of code. And now we scale up to really the scale that we're used to working with when we're dealing with Spark. So 1,000-class classification problem, millions of examples, tens of thousands or even hundreds of thousands of features. We're able to train this pipeline end-to-end in 90 minutes on a 100-node cluster. And one of the things that's really nice from an engineering perspective is that if I decide, instead of doing a linear solve to the system that comes out at the end of the pipeline, I want to do a weighted linear solve. Changing that is really changing one line of code in my pipeline definition. So it's a different logical learning algorithm that I want to use here. And adding 100,000 more texture features is also just a handful of lines of code. So these things are, by design, very modular and easy to kind of change from the developer's perspective. OK, so the rest of the talk, and this was in my talk title, I want to talk to you about optimizing KeystoneML pipelines. So when we say optimization, what do we mean? So when we write down these pipelines, they may actually be built out of many different Spark jobs. So each, one stage of, say, gradient descent is a Spark job. And so if I have many stages of featurization, different solvers throughout one of my pipelines, I have lots of Spark jobs that are somehow related. And what Keystone allows you to do is tie together these Spark jobs with this high-level API and tell the system, this is the plan for my entire sort of program execution for training one of these things end to end. And this enables, we think, a very rich space of optimizations. So one of the first optimizations I'm going to talk to you about, and I'll talk to you about a specific example, but this is a very general idea, is automated machine learning operator selection. So if the user writes down at the end of their pipeline, I want to use linear solve as my machine learning sort of model that I want to fit here. It turns out there are a lot of different ways to solve a linear system. Many different algorithms exist. They have different properties. There are different places where some work and others work. And our system has a cost model built in that I'll talk about in some detail to pick between the best algorithm to solve this particular problem. And we have this sort of cost model based operator selection built into several operators throughout the system. The other cool optimization that we do, again, with this idea that we're going to be running sort of multiple Spark jobs to fit a single pipeline, is what we call auto-caching for iterative workloads. And so the big idea is if we write down one of these pipelines, we can see pretty quickly that, say, SIFT extractor is going to be reused multiple times. The output of that operator is going to be reused multiple times by downstream elements in the pipeline. Similarly, dimensionality, reduction, and normalization also have that property. Further, many of these algorithms, in this case, least squares LBFGS is a good one, is going to loop over its input data multiple times. It's an iterative algorithm. And so by knowing that, we can figure out where the right place to materialize intermediate data is within this pipeline to save time at execution. Good. So the KeystoneML optimizer works kind of like this. So we use sampling techniques and build up a cost model that projects resource usage by each stage of the pipeline. So we start with our input. It's a 5,000 JPEG images. We know roughly the size. And then we take a sample of it, and we run it through the pipeline. We just a small sample of images, and we use that to project the memory requirements, the CPU requirements, the network requirements of each of these operators in the pipeline. And we build up this kind of table of information that we use for optimization. So the utilization is tracked through the pipeline, and then we make decisions to minimize the total cost of execution. So the first level of decisions that we make are in the case of this particular pipeline, these three operators, PCA, Fisher vector, and linear regression, all have multiple implementations in the system. And so we're going to pick the implementation that's going to run best given our problem shape and size and the size of our cluster. The other thing that goes on is this resource awareness, this knowing how much intermediate state I want to materialize. And you can see in this example that even a small input data set, just 500 megabytes in size, throughout this pipeline, the intermediate state can blow up very big, a few orders of magnitude bigger, in fact. And it might make sense, actually, to cache that intermediate state if we can afford it in our cluster. And so the system is then aware of these requirements and optimizes for this. The whole KeystoneML optimizer is actually built on Catalyst, the Spark SQL optimizer. We have our own completely different set of rules than what goes on in Spark SQL, but we're reusing that great piece of software from the Spark community to drive a lot of this. Great. So now let's talk about choosing a solver. So when we're writing down, and this is an example of a specific per operator optimization that we do. So when we're writing down linear regression is this logical kind of statement. It says, I want to find the x which minimizes this whole equation. Okay, so this is a regularized variant. Where A, in this case, is our data matrix. So it's got n examples in it in d dimensions. X is the model that we're trying to fit, so we know how big that thing is. And B is this is our labels in this case. So there are k classes in my multi-class linear classification problem. B is going to be this sort of one-hot encoded matrix. So first observation is that data sets themselves have a large number of degrees of freedom. So not only is n and d an option, so or k, the sort of problem size, so how many examples do I have, how many features do I have, but I also have to think about sparsity. So if my data set has a lot of zeros in it, as is often the case in, say, text classification pipelines, then the right solution or the correct solver for this particular problem is going to change. So sparsity is an important statistic of the data set that we want to track and use to make decisions. Another thing that varies among data sets is this thing called condition number. It's a mathematical concept that talks about how easy our system is to solve. And then the platform, of course, has a number of degrees of freedom. So how big is my cluster? How much memory does it have? How many CPUs? How many nodes? How fast is the network between these nodes? These things can have a big impact on how fast it is to solve your problem. The nice thing for us, though, is that the linear solvers are well studied and they're predictable in their behavior. So we can write down a cost model for how these things work. And so here's some sort of empirical evidence of that. So let's talk about three solvers, and all three sort of distributed, run in the right way on Spark. So first is an exact solver, which does this QR decomposition, which is a linear algebra technique to really solve sort of the exact system. Another is a block solver that we developed based on block coordinate descent, and the third is an LBFGS algorithm, similar to the one that ships in MLlib today. So we ran on two different data sets. First is this Amazon product reviews data set, which is a big data set of product reviews, 65 million of them. The second is this Timit data set, which is used in phoneme classification. So the big difference between these data sets is that while Amazon is really big, it's got 65 million examples, it's super sparse, it's tiny. It's tiny in terms of actual number of non-zero entries per record in the data set. Timit, on the other hand, is super dense. Every single one of those features is non-zero in Timit. So it's this big, dense system that we need to solve. The big takeaway from this graph is that the exact solve works well for a small number of features, particularly in the dense case. So if you're under about 4,000 features, no reason to use one of these iterative approximate algorithms. Just take one pass over the data set and do QR on it. But for sparse problems, this LBFGS algorithm and other sort of accelerated gradient methods are going to work much better than your dense algorithm. So this block solver is particularly well suited for dense algorithms, but on the sparse problem, it's 2 orders of magnitude slower. And the block solver scales well to these big dense problems. So not shown on this graph, we've run the block solver out to about 500,000 features on this Timit data set. So really, really wide feature spaces. And it works nicely in sort of memory constrained environments and continues to sort of scale while these other solvers may not. So good. So now let's compare the performance of these solvers to sort of other state-of-the-art distributed learning systems. So we compared KeystoneML with two systems. First is Vopal-Wabbit, which is a specialized system that works especially well for large sparse problems. And the other one is SystemML, which is a general purpose optimizing ML system that does some really, really amazing sort of low-level optimizations, but is running a specific algorithm in this case, which is conjugate gradient method. To solve the linear system. So we did two problems, again, this Amazon problem, and then a binary version of this Timid problem because the SystemML implementation didn't support a multi-class solver. So the higher order bit from the results I'm about to show you is that KeystoneML is able to achieve high performance by both pipelining featurization and solving, and by adapting to workload changes. So first, let's look at this Amazon number. Compared with Vopal-Wabbit, KeystoneML is about 3 to 4x faster on this sparse Amazon data set. And a big part of this, the reason why KeystoneML is faster is this very reason of pipelining the featurization and solve. There's no sort of intermediate state being written out to disk before you load up and launch Vopal-Wabbit. Similarly, we get to this dense problem, this large binary Timid thing, and KeystoneML is about an order of magnitude faster than Vopal-Wabbit, and it's because we use the right algorithm and the right data structures to represent our dense data, and Vopal-Wabbit is really just using LBFGS out of the box and on its sort of general purpose data structures. With SystemML, the outcome is basically reversed. So Keystone is quite a bit faster than SystemML on the sparse problem, again, because this conjugate gradient method is not working extremely well with the sparse data. It's really designed to work well with the dense data. But on the binary Timid data set, Keystone is about 3 or 4x faster than SystemML. And again, it's because it's choosing the right algorithm for the job and pipelining this featurization along with the solve. If we just compare solver performance for this particular task, the systems are within a factor of 1.5 of each other. Keystone's a little bit faster, but it's sort of close enough that I could see either system winning on either problem. So great. So let's talk about. So I've given you some motivation for the sort of per operator level optimization that we're doing in Keystone. So that was one example, linear solve. We're doing that with a bunch of other logical operators in the system. And now let's talk about how we decide what to save. So this is this idea of how do we manage intermediate state in these pipelines. So again, our pipelines are going to generate lots of intermediate state. So again, in the previous few slides ago, I showed you this table where the data set blows up from half a gigabyte to 300 gigabytes after featurization. These items that I've circled on this slide are iterative algorithms that are going to potentially need to reuse the input state many times. And so we need to answer the question, how do we determine what intermediate state do we want to save for later given a fixed resource budget? So given a fixed amount of memory on our cluster, how do we decide what to keep and what do we throw away? And the other question is, can we adapt to workload changes? So as the number of examples in our training data set or the number of features because of some change to some hyperparameter higher in the pipeline, does that change the properties of what the right thing to save is? And can we adapt to that? So we formulate this as a simple graph problem. This is a caching, what we're calling the caching problem. And we write down our pipeline as a DAG that looks something like this. This is just an abstract example. And first is we make an assumption about our execution model, and that is that we're operating under Spark's execution model, which is the output in this case is computed via depth-first evaluation of this DAG. And I've annotated the DAG with runtimes on the top, so 60 seconds to run node A, and 50 gigs is the size of its output. Caching in this case, if you put a .cache after the RDD in each of the, if you think of this as sort of an RDD lineage graph, caching basically truncates a path after its first visit. So if I think about how I compute my output, I'm going from node E to C to B to A, and then executing in order, and then I go back down the branch of node that includes node D. So if I cache node B, I only have to compute it once, and in subsequent iterations, subsequent visits to that node, I only have to, I can read it from memory, I don't have to recompute it. Great. So the goal here is to minimize execution time, subject to some memory constraints. And so I can see very clearly that if I pick a cache set where I cache everything in this graph, I can minimize my execution time down to the level of finishing the entire pipeline in 140 seconds. So that is, I cache everything, I just write down everything I ever might need again, no matter what, and I can minimize my total runtime because subsequent visits to those nodes aren't going to incur any runtime. But that strategy is going to be bad because it's going to require me to use the maximum amount of cluster memory possible. So 340 gigs in this case. If my cluster doesn't have that much memory, I'm sort of out of luck. On the other side, I could cache nothing, and I, of course, pay to recompute each of these nodes every time I visit them. And then it turns out there's sort of a sweet spot in the middle where if I only cache node B, I achieve the minimum runtime without paying that full memory penalty. But if I still don't have that, I can still get some benefit by only caching node A. I won't take you through the sort of solution to this problem, but picking the optimal set turns out to be pretty hard. And we implement a greedy caching algorithm that works pretty well in KeystoneML, and we've tested it on a bunch of different data sets. So let's take a quick look at end-to-end performance of the system. So first, we're going to take a look at 4 different data sets in 3 different domain areas. So first, Amazon, which is this text pipeline I've talked about. Timid, again, phoneme classification. ImageNet and VOC are image classification pipelines. And so these all have varying number of training examples, lots of different features that we compute throughout these pipelines, sometimes only tens of thousands of features, sometimes hundreds of thousands. The raw size of all these data sets is actually not that, not that big. It's sometimes half a gig up to 8 gigs. But the important thing is that the featurization process actually can generate quite a lot of intermediate state. So in this case, in the case of the Timid pipeline, I start with an 8 gig data set, and I blow it up to an 8 terabyte data set before at solve time. And so that is the size of the system that we have to solve with Keystone. And that might not even fit in cluster memory, so we have to use some sort of clever algorithms to solve the system quickly. So great. So now to get to end-to-end performance on these data sets. So the Amazon pipeline was inspired by Chris Manning's group at Stanford. We don't have a reported accuracy on this data set, but we verified it worked well on a smaller data set. The 3 data sets that we spent a lot of time on were this Timid data set, ImageNet, and VOC, where we matched the pipeline that other academics had written down as close as we could, and we made sure that we got the same statistical performance as they did on these data sets. So this was a best effort recreation of something that existed in the literature. Now, the two kind of key points here are first, on the image classification pipelines, we were comparing against highly optimized single node systems, and we ran on in the case of VOC, a 16 node cluster, in the case of ImageNet, a 64 node cluster, and we get substantial speedups over the reported times for these pipelines on these highly optimized systems. Not super linear, not anything like that, but still pretty good, orders of magnitude, and stuff that could make a difference in the working life of a data scientist, somebody who's building these things for a living. The other number of interest is this Timid number. So it actually looks like Keystone is a bit slower than the reported system on this slide. And that's true, but we ran Keystone on 64 nodes in Amazon EC2, and this is by comparison with a 256 node Blue Gene supercomputer at IBM that has actually 8 times the number of cores as Keystone. So on an eighth the resources, we're able to achieve 90% of the performance. So this is a distributed system. We're getting the same thing, and that code base is pretty highly optimized. Great. So now let's take a quick look at the scalability of the system. So Keystone scales pretty well, especially on this ImageNet pipeline, and I'm comparing this to scalability over 8 nodes. We didn't really feel like waiting a week to run some of these things on a single node. So we get pretty close to ideal speed up. In Timid and Amazon, we of course tail off a little bit in terms of scalability, and so we of course wanted to dig in and figure out why aren't we seeing that. So first, in the case of this Timid pipeline, The reason we stopped scaling is not due to featureization. It turns out to be the solve. So we're using this block coordinate algorithm to solve this pipeline at this scale. And while it's communication avoiding, the one big thing I hope you take home from this conference is that distributed machine learning is hard and communication is inevitable. And so you have to be very careful about how you control that. In this case, we pay sort of close to lower bounds in terms of communication, and the solve scales with log of the number of machines. On the Amazon pipeline, we see a bunch of overheads based on sort of data loading and sort of evaluation. This is stuff we probably could make faster if we wanted to, but at the end of the day, we're able to build a text classifier on 70 million training examples in 3 minutes, and we think that if you threw a billion training examples at it, it would continue to scale right up. So we're pretty happy with that. So good. So I think I'm out of time, unfortunately. I'm happy to take one question. I'm sorry I didn't leave more.
Cool.
So great.
You guys give him a big hand first.